This is the Introduction to Polar Graphing. Back when you were in Algebra 2, just a mere babe in your mathematical progress, remember you learned how to graph using x and y. So if you started from the origin, you'd go x units to the right and y units up, and you'd have a point x, y. Now we're going to learn another way to name or label this point. This is going to be based on two things. Its distance from the origin, which we're going to call r for radius, and its rotation from the positive horizontal axis, which we're going to call theta. So instead of calling this point x, y, we're going to call it r theta. So if we look down at this graph below, you'll notice that we don't have a graph that goes in the x and y direction now. We have a bunch of concentric circles, which we'll use to find the radius, and then we have a bunch of rays, which we'll use to find the angle. I wanted to find a couple of terms. The origin, 0, 0, can now be called the pole, so we refer to it as the pole. The ray at 0, that's this dark bolded line here that's labeled 1 through 10, that is called the polar axis. Now I'm going to show you kind of how this works by adding an arrow to the polar axis here that I can kind of manipulate around. So right now, this little white dot here is at the point 0 degrees or 0, 10, 10 units out. So 10 and theta is 0. So r is 10, theta is 0. Now if I move this around, r is still 10. R is 10 now, and theta is 45 degrees. R is still 10, and now theta is 90 degrees. R is still 10, and now theta is pi, or 180. Now notice, we're not saying negative 10, because right and left do not denote negative and positive anymore. The direction is described by the angle. So this is actually positive 10 in the, but 180 degrees around, or positive 10 pi. So now we're at positive 10, 270, and back to positive 10, 0, or positive 10, 2 pi. And if we were at a smaller angle, we could say now we're at 6, 30 degrees, or 6 pi over 6, and so forth. So that's how this works. I'm going to delete this now, this little ray, and let's label some points. So using r theta, what we're going to do is when we see this, the first number, that's our radius, we're going to go out along the polar axis that many units, then we're going to rotate along that particular circle till we get to the angle. And I just realized we need to label these axes, or these rays, first. So you'll recall that we're going to do this in radians, because radians are going to be what you're going to use in calculus. So I want you to be as familiar with radians as possible. They're harder to think through than degrees, but you'll get better at them with practice. So we have 0 radians if we're going in the positive horizontal direction. Over here to the negative side, although it's really not the negative side when we're in polar form, but over on to the left, then we have pi radians halfway around. If we get all the way around, we could also call it 2 pi. If we go straight up, we're at 90 degrees, which is pi over 2 radians. If we go straight down, we're at 270 degrees, which is 3 pi over 2 radians. If we go halfway between 0 and 2 pi, and pi over 2, we're at pi over 4. If we go, each of these rays are actually 15 degrees apart, so 2 rays over, that's 30 degrees. 30 degrees is pi over 6, because 180 is pi, and 180 divided by 6 is 30. Pi over 3 would follow pi over 4. So those are all of our quadrant 1 special angles. Now if this is 1/3, if we go another 60 degrees here, now we're at 2 pi over 3. Then we are at 3 pi over 4, and at 5 pi over 6. Notice that we are 1 short of being 1 pi. So 2 pi over 3, 1 more pi over 3, and it would be 3 pi over 3, we'd have pi. 1 more pi over 4, we'd have 4 pi over 4, it'd be pi. 1 more pi over 6, we'd have 6 pi over 6, and we'd be at pi. So notice this is 2 over 3, 3 over 4, 5 over 6. Now, if we go into the third quadrant now, we are a little more than pi. So when we go 1/6 again here, 1/6 pi, we're going pi plus another 1/6 is 7 pi over 6. So we're at 7 pi over 6. Pi plus another 1/4 is 5 pi over 4. Pi plus another 1/3 is 4 pi over 3. Then when we go, and so notice now we're 7 over 6, 5 over 4, 4 over 3. Now when we go into the fourth quadrant, notice that we have 6, 4, 3 in the denominator. 3, 4, 6, 6, 4, 3. Now we're going to have 3, 4, 6 again. So the first one is 5 pi over 3, then 7 pi over 4, and then 11 pi over 6. Each of these is one fraction less than being 2 pi, because 5 pi over 3, if I added 1, would be 6 pi over 3. That would be 2. 7/4 is 1 shy of being 8/4. 11/6 is 1 shy of being 12/6. So here's our pattern of special angles. So now that we have those labeled, we're going to go out 5, and then we're going to rotate along the 5 radius, all the radius, everything on that circle that has a radius of 5, till we get to pi over 3. So that would be this point right here. So we're going to lay, that's point A, 5 pi over 3. Then we're going to go out 6, or out 8, and we're going to rotate negative pi over 6. Well, the positive direction is counterclockwise. The negative direction is clockwise. So we're going to go downward. We're going to rotate down this way, and this is going to give us our 8 negative pi over 6. Now notice that 8 negative pi over 6 is the same thing as 8 positive 11 pi over 6, because we could have rotated all the way around this way to get there, and that would have been 8 11 pi over 6. So a point can have more than one name in polar form. Okay, C, negative 4 pi over 2. Ooh, that's tricky. Well, this is positive 4 pi over 2 right here. So where's negative 4 pi over 4? Well, negative 4 is just the opposite direction. It's down instead of up. So I can go positive 4 to pi over 2 and then just flip 180 down to get to the point that I want to be at right here. That would be point C. Now another way you can do it is I can say, well, this is the positive 4 direction. If I wanted a radius to be negative 4, I would go the opposite way. So 1, 2, 3, 4. So that would be negative 4, starting out at negative 4 instead of positive 4. Then I want to rotate pi over 2 in the positive direction. So if I wrote pi over 2, that's 90 degrees. In the positive direction, I'd end up there at C. The negative radius is tricky. Okay, so let's look at negative 7, negative 2 pi over 3. So positive 7 would be here. If I did positive 7, negative 2 pi over 3, well, there would be 1 pi over 3, and there would be another pi over 3. But that's positive 7, negative 2 pi over 3. I would have to go the opposite direction all the way up to here now to get where I'm supposed to be. This point right here. Now another way to do it, and I think an easier way, is to think, let's do the negative 7 first. So positive 7 is over here. Go 180 degrees the opposite direction. There would be negative 7. Now rotate negative 2 pi over 3. That means rotate in the clockwise direction. So negative 2 pi over 3. There's a pi over 3. And there's my next pi over 3. So there it is at D. So the negative ones take a little getting used to. Hopefully that makes sense. You might want to play that over again on those C and D if it didn't make sense. E, 0, 3 pi over 4, radius of 0. Well, if the radius is 0, I'm not going anywhere. I'm right on the pole. I don't move off the origin. So here is point E right here. It could be 0 any angle, and it would still be right on the origin or on the pole. Then 2, 0 means we have a radius of 2, but the angle is 0. So that is a point on the polar axis at 2. And that's right there. Now I'm going to change, it says other ways to label point C, and I'm going to do point C, but I'm also going to do another point, because point C is kind of an unusual one. Point C, here's the point, negative 4 pi over 2. I could have also called it positive 4, negative pi over 2. I could also call it positive 4 all the way around here, positive 4, 3 pi over 2. And I could also have called it negative 4, so go in the negative direction, 1, 2, 3, 4, negative 4, negative 3 pi over 2. Now if you notice on all of these points, including the original, which was negative 4 pi over 2, that all I did was switch the negative sign from r to theta or vice versa. But that isn't always how it works. That happens to work just because it's a 90-degree angle. It doesn't always work. So we're going to look at point B. So if we look at another way to label point B, B is right here. We have 8 negative pi over 6. We could also call that 8 11 pi over 6, which we talked about earlier. And I am going to downsize this. We could also call it negative 8. So let's do something with negative 8. Go over to negative 8, which would be over here. And we want to get to point B. So if I went in the positive direction, how far am I going? Negative 8. I'm going 5/6 of the way around. Okay, 5/6 of the way around of pi. So from 0, so remember a semicircle is pi, so I'm going 5/6 of pi. So this would be negative 8, positive 5/6. Erase that. Negative 8, positive 5/6, 5 pi over 6. Or negative 8, and then if I go in the negative direction, so if I go negative 8, let me push this up a little bit, negative 8, if I wanted to get to point B and I'm going in the negative direction, how far have I gone? I've gone all the way around pi units and then another 1/6, so this is 7 pi over 6, but in the negative direction. So this is negative 7 pi over 6. So notice each one, my coordinates, all of my radius, all of my angles are completely different numbers. Some are positive, some are negative. They're all something over 6, but they're all completely different. They're not opposites of each other like they were for point C. So this is probably more typical of what you find when you write different coordinates for the same point. Now the last thing I want to do on this page is I want to go back and forth. If I know the coordinates of the point in polar form, could I put it into what's called Cartesian form? Oh my gosh, where did Cartesian form come from? Well, we have two different ways of describing an XY graph. One of them is to call it rectangular form, because basically you make a rectangle when you graph and plot X and Y. The other one is called Cartesian form. It's the same graph. It's an XY graph, but it's called Cartesian form after a Frenchman named René Descartes. And so he's the one that came up with the idea of the XY coordinate plane, so that is named after him, called a Cartesian coordinate plane. So if you hear me say either rectangular or Cartesian, I'm talking about XY. So I want to go from r theta to xy, or xy to r theta. So how do I do that? Well, if we go back up to the top, let's do something we've been doing since the beginning of the year. We're going to make a triangle, a right triangle. So up in this upper left-hand corner, I'm going to drop a perpendicular line down, and all of a sudden, I'm doing trigonometry again. Yay! So x is the horizontal leg of this triangle, and y is the vertical leg of this triangle. And let's think of some relationships that help us to connect x and y to r and theta. One of those relationships, probably the first one you think of, is Pythagorean theorem. I know that x squared plus y squared equals r squared. And the other relationships that may pop to mind quickly are SOHCAHTOA relationships. Sine of theta is equal to y over r. Cosine of theta is equal to x over r. And tangent of theta is equal to y over x. So if I'm going from polar to rectangular, in other words, I know r and theta, and I want to find x and y, basically I want to find an equation that I can plug r and theta into and figure out what x is, and I can plug r and theta into and figure out what y is. Those would be the first two things that we wrote for SOHCAHTOA, sine and cosine, because sine relates theta and r to y, and cosine relates theta and r to x. So if I were to take the first equation here and solve it for y, I would have y is equal to r sine of theta. If I were to take the second equation here and solve it for x, I would have x equals r cosine theta. Those are the relationships that move us from polar to rectangular form. Now from rectangular to polar, I know x, y, and I want to find r and theta. So I need to take an equation that has x and y and use it to find r, and x and y and use it to find theta. And being the brilliant students you are, you probably figured out I'm going to use the other two relationships. I'm going to say that r is the square root of x squared plus y squared. And I'm going to say theta is equal to inverse tangent of y over x. Now you've got to recall that from when we're talking about tangent, that when we look at our four quadrants, remember that tangent is positive in quadrants 1 and 3, and it's negative in quadrants 2 and 4. And when I do inverse tangent, I get an angle that's between negative 90 and 90, or between negative pi over 2 and pi over 2. So that means if I do inverse tangent on the calculator, I can only get a quadrant 1 or a quadrant 3 angle. What happens if I want a quadrant 2 or a quadrant 4 angle? Well, I need to add 180, or in this case, add pi. So plus pi if theta, oops, that's a Q, not a theta, if theta, oh, I went blue. If theta is in quadrant 2 or quadrant 3. And I should say is in, not in. So I'll change that. Is in. That wouldn't have been a half point anyway. Get over it. All right. Now that I have my relationships, I'm going to use these now to do the problems at the bottom of the page. So to put a point from rectangular into Cartesian form, I'm going to use this relationship. X is equal to r cosine theta, y is equal to r sine theta. So my r is 5. So I'm going to say x is equal to 5 cosine pi over 3. And y is equal to 5 sine of pi over 3. Making sure your calculator is in radian mode. Remember, if you're on the Inspire, you can just kind of cursor up to the upper right-hand corner of your calculator, and there's a little battery symbol, and you can look and see. I should show you right there. You can go up here and see if it says angle radian or angle degrees, so you would want to do that. If you are on the TI-84, you'll want to go to mode and check and see that you're in radian mode. So anyway, if you calculate 5 cosine pi over 3, you end up with 2.5. And when you do 5 sine of pi over 3, you end up with 4.33, etc. Let's double check and see if that looks reasonable. This is the point 2.5, 4.33 in x and y. Does that equivalent to the point 5 pi over 3 in polar? So if we go back up here, here's the point 5 pi over 3. It's point A here. Now let's imagine that we have an xy graph superimposed on top. So here would be my y-axis. I'm drawing it in with a red dotted line. That would be y. And my x-axis would be in this red dotted line in the horizontal direction. That would be my x. And if I were to want to plot the point 2.5, 4.33, I'd go 2.5 units in the x direction, which would be right here, 2.5. I'd go 4 units in the y direction. So that would give me about here. This would be 4.3 right here. And if I went directly across and directly up and down, look at that. I get right there to the point A. So point A has as its rectangular coordinates 2.5, 4.33. Okay, so those are the rectangular coordinates for the polar point. Now I want to go the other direction now. I want to put -5, -2 into polar form. So let me start by locating -5, -2 on the graph up here. And it is always, always, always a good practice to make a sketch of whatever it is you're trying to find, because you will know then if your answer is reasonable. So if I go -5, basically going out a unit, 5 radius units in the x direction, so there's my -5, and go 2 radius units down to get to -2. And it's very hard to do this because the circles make it hard to make a straight line, but basically I'm going down, straight down, and straight across. That looks reasonably rectangular. And so I'm looking for a point right down here. So this is my point -5, -2, but I want to name it in polar form, which means I'm looking for a radius length here. There's my r. And I'm looking for a theta that goes around like this in radians. Okay. It's not going to be a special angle. I'm going to get it in decimal form. So the first thing I want to do is just to get a feel for how many decimal values. What are the decimal values of these radians? So remember that 1 radian is about right here, just a little bit before pi over 3. 2 radians is about right here. 3 radians is close to 3. There's 3 radians is about right there. 4 radians I think is about right in here. I might be wrong on that. 5, 6 radians. You know, I may not put the 4 and the 5 and the 6 because I'm not sure quite where it fits in relationship to the others, but what we did in class, and I think I'm going to stop, pause this, and go ahead and add the decimal values to all of these pi over 6, pi over 4, and so forth, so you know kind of approximately where those are. So I will put those on and I'll be back with you momentarily. Okay, I am back. Notice here that I have the decimal equivalents for all of these different special angles. Pi over 12. I don't think we talked about pi over 12, but that would be halfway between pi over 6 and 0. And I put pi, so I just threw that on there. The other ones that are missing are also something over 12, but I'm not going to put those in. This is 0.26. Pi over 6 is 0.52. Pi over 3 is 1.05, and so forth and so on. So you can pause the video and add these on, but this will give you a better sense of the numbers that we need. So for example, if I'm doing a quadrant 3 angle right here, that's what I'm going to need, a quadrant 3 angle for this particular thing. If I draw this back in here, if this is my r and then this is my theta going all the way around to quadrant 3, notice I'm going to need a radian value that's somewhere in between 3.14 and 3.66 radians. And we could actually put in, we've done the 1, 2, and 3, we could put in the 4. 4 would be pretty much close to here, probably. 4 is in there in quadrant 3. 5 is going to be before you get to 5 pi over 3. 5 would be around there, and 6 would be probably around here. So there would be about 4, 5, and 6. So that gives you kind of a sense for the number of radians. Okay, we're going to go back to finishing this problem then. So if we look down here, I want to use my other two relationships. R equals the square root of x squared plus y squared. Theta equals inverse tangent of y over x. So r is equal to the square root of 25 plus 4, which is the square root of 29, which is approximately 5.4. That looks quite reasonable if you look up at our graph. If this is 5 units right here and this is 2 units, that makes very much sense that this this hypotenuse of that triangle would be 5.4. That looks very reasonable. Also, you can see that it extends just a little bit past the 5 radius circle here. Then when we do theta, theta is inverse tangent of -2 over -5. Make sure you do y over x and not x over y here. You get 0.38. When you look at the graph here, 0.38 is somewhere in between pi over 12 and pi over 6. You've labeled those numbers. And that means that, and the angle I want, though, is over here in quadrant 3. So notice how far apart they are. 180 degrees or pi units apart, pi radians apart. So I need to add pi to get to the angle I want, because the angle I was given on the calculator is a quadrant 1 angle, but I want a quadrant 3 angle. And I know I want a quadrant 3 angle because my point is -5, -2. It's in quadrant 3. So that's your clue. Also, make a sketch, make a sketch, make a sketch. Very important. So if I add 0.38 plus pi, let me do that very quickly on my handy dandy calculator here, I get about 3.5. So it's approximately 3.5. And I'm going to look and see, does that look like reasonable sense? Yeah, 3.5 radians. That looks very reasonable because I had figured this was 3.14 and this was about 3.6 something. So 3.5 looks very reasonable for this. So this point can also be labeled as 5.4, 3.5 radians. And I'm putting radians just because both of those numbers are decimals, just to remind you that that second number is the angle. Okay, we're getting close to being done. This is a long notes, I know. So now we'll go to the other page here. Notice I have the grid here, and we do need to label one thing on this grid. We don't have a polar axis labeled, so I'm going to label my polar axis here. And let me just do every 2 tick marks. So go 2 tick marks out, that would be 2. Another 2 would be 4, 6, 8, 10, 12, and 14, if you go all the way out. Okay, so we have our polar axis now. Oops, I labeled 12 in the wrong spot. I think some of you probably are screaming half point about right now. So 12, 14, there we go. I want to recall, we were going to graph this equation, r equals 10 cosine theta. And you might think, oh, a cosine graph, a cup that points up. I know that. And if it's got a 10 for an amplitude, that just means it's a taller cup that points up. Well, that's what it would be in xy form. But if it's in r theta form, it's a completely different looking graph. But let's start with what we know about cosine, because we're going to need to plot some points. So we know in xy form, if we have y equals cosine of x, basically we start out high. Oops, I almost did sine instead. We start out high, it curves down, and it comes back up. And it completes its cycle in 360 degrees, or 2 pi radians. It's halfway through its cycle at pi. It will cross the x-axis a fourth of the way through its cycle at pi over 2, and then at 3 pi over 2. So I know from this graph that cosine of 0 is 1, cosine of pi over 2 is 0, cosine of pi is -1, cosine of 3 pi over 2 is 0, and cosine of 2 pi is 1. So I'm going to use that fact to help me to plot a few of these points rather quickly. So if I have r equals 10 times cosine theta, cosine of 0 is 1, so 10 times that would be r is 10. Let's go down to pi over 2. Cosine of pi over 2 is 0, so this is just going to be 0. Cosine of pi is -1, so 10 times -1 is -10. 3 pi over 2, cosine theta is 0, so this is just 0, and then and when I get to 2 pi, I'm back up to a +1. Cosine of 2 pi is 1, so times 10 is 10. Now, once again, I'm going to pause and fill in, but basically what I would want you to do is, we did this in class as a group, 10 cosine pi over 6, 10 cosine pi over 4, 10 cosine pi over 3, and fill in those points. So let me pause, and I will get those on there for you. Okay, there we are. Those are the table of values. Notice everything that ends with has a pi over 6 in it is all either positive or negative. 8.66, that's the square root of 3 over 2. The 7.1 goes with the pi over 4, and I only have one that has a 4 in the denominator. That's the square root of 2 over 2, or 1 over the square root of 2. Pi over 3 is when we have cosine of theta is equal to 1/2, so you multiply that by 10, you get 5. And these also are multiplied by 10, because it would be 0.866 and 0.71. Notice also that cosine is positive in quadrant 1 and 2 up until you get to pi, but then when you get, oops, I think I did, no, I was wrong, sorry. It's positive in quadrants 1 and 4. So from 0 to pi over 2, it's positive, and from 3 pi over 2 to 2 pi. So cosine's positive in these two quadrants, and it's negative in quadrants 2 and 3, so that's why all the numbers in the middle are negative. Let's plot some points. So we have the point 10, radius 10, angle 0. That would be right here. Then we have the point radius 8.6, pi over 6. So that would be about right there. We have 7.1 pi over 4. That would be about right there. We have 5 pi over 3. Then we have pi over 2, 0, which would be at the pole. I think I have that the wrong, this point was wrong. 5 pi over 3 right here. There we go. Another half point missed. Oh, how sad. Okay, then we get to the negative one. 2 pi over 3, negative 5. So I'm going to go negative 5. 1, 2, 3, 4, 5. And then I'm going to go 2 pi over 3. So that takes me over here to where 5 pi over 3 is, right there. Then I have negative 8.66. So 1, 2, 3, 4, 5, 6, 7, 8, almost to 9. And I'm going to go around 5 pi over 6. So that's all the way over here to the 11 pi over 6. So right there. And then I have, the next one would be pi negative 10. So if I go negative 10, that would be out to here. And then I go pi all the way around here. Look at that. I end up right back on where I was to start with at 0, 10. If I go negative 8.66, so let me kind of find my 8.6. That would be about right in here. Negative 8.66, and then go 7 pi over 6. So that's all the way around plus another 6. Look at that. I'm ending up on a point that I already plotted. It turns out that once you get to pi, everything starts to repeat. And so you would just make another loop around here. And if I asked you to describe, to connect these in sort of a smooth curve, what do you think this is? I think most of you kind of recognize that this looks like it's a circle. And it is a circle. That's probably the nicest one I've drawn all day. So it's a circle. So the graph 10 cosine theta in polar form is a circle, not a sinusoidal curve like we had before. Now let's look at how to graph this on the calculator, and then we'll finish up the notes here. I have some instructions down here for the Inspire, and I also have some instructions that 84 users can use to pick up. So on our graph, I'm actually going to insert another graph page so we can start over. So let's, oops, I don't want a geometry page, I want a graphs page. Okay, there's a graphs page. So this is what yours is going to look like. Notice that it's an f of x, and I want to have an r of x down here. So the first thing I'm going to do is go to Menu, Graph, Edit, Entry, and then find Polar. That switches my entry line down here to polar form. And yours will say R1 because this will be the first one you've done. This is the second graph I've done in this document, so mine says R2. The theta tells me how many values of theta are going to be plotted from 0 to 6.28, and it's going to be plotted every 0.13 theta. So a lot more points than what I plotted in our hand-drawn graph. Now to type in the equation, of course, you're going to type in your 10, and cosine is under trig. And actually, if you hit the trig button twice, it'll automatically jump it over to cosine. You can push enter. There's two places to find a theta. One is under the pi. You go under pi, and then you have to go over five things. The trouble with this one, though, is every time you open this button, it'll automatically go to pi, and then you have to arrow over 5. If you go to Control and the little book thing, the catalog, if you select pi, then every time you open catalog, that same thing, Control Catalog, it'll be on pi already unless you change and get some other symbol. So that's probably the one I would prefer to do because I don't have to move as many keystrokes. Then push enter, and you have this lovely circle graph. Yours is probably blue. Mine's red because it's the second graph I did. Now we can trace this graph, and if you go to Menu, Trace, Graph Trace, you'll notice that kind of wherever you put your cursor, you can kind of move it around. Or it'll just be on some point. Now I'd like it to start with my first point on my list, which is at 10, 0. So I'm going to just type in 0. So I'm just going to go type 0, enter, and it'll automatically, oops, I just got it off of there again. Let me do that again. 0, enter. Notice now it is automatically, if you look at the bottom down here, I'm going to try to do this without touching the graph, you'll see my coordinates 10, 0, and you see that the point is right over here on the graph. Now, if I right arrow, it's going to take me around at 0.1 radian at a time. So notice how the radius is changing. The radius is smaller each time because this point is getting closer and closer to the origin. It's taking me around here. There's 1.5 radians. 1.57 is pi over 2. I could also type in pi over 2 if I wanted to, pi divided by 2, and notice it would give me, oh, I didn't get the divided by 2 somehow, divided by 2, enter. So there, that gives me 0, 1.57 radians, that's pi over 2 exactly. And I can keep going around. Now it's gotten me off my nice numbers, but basically now it's taking me to negative values for the radius. And so this is basically saying I'm at 2, oops, shoot. I am at, I want to go around here. Where was I? Back over here. So the first is R. So R is -5 at 2 radians. So remember 2 radians would be out from the center. 2 radians would be in the quadrant 2. Well, I don't have any points in quadrant 2. So that's why this point is showing me a negative radius, because if I had a positive radius and I was in quadrant 2, I'd be over here, but there's no points over here, so that jumps me back over to this negative radius, and I'm actually in quadrant 4. Okay, for help on your homework, there's a worksheet posted called the Intro to Polar Graphing Worksheet, which is also posted in Google Drive, and this, along with this video, there's a video that says Intro to Polar Graphing Worksheet Tips, and that's to go along with the worksheet if you have trouble with the worksheet, and you may very well have trouble with some of the problems on the worksheet. So that is all. I know this was a long video. Hopefully it was helpful.